All right. Good morning, everyone. Welcome back. Obviously, this is week 2, lecture 1. Just didn't change my numbers on that. No big deal. 5.1 and 5.2, we said last time are going to be due on the 3rd because we had finished those. We finished everything except for the calculator-based problems from 5.2, which will take us about 10 minutes. It's the first thing we're going to go over, but again, it's simply typing things in a calculator, and it's only 10 minutes worth of material, so I don't feel bad about saying that that's still going to be due on the 3rd. And then you'll notice that I don't have anything about 5.3, and I'm not going to add 5.3's due date today because it's not going to be due in a week. It's going to be due a week from next class, and that's because 5.3 is a pretty lengthy section, and it's going to take us just over 2 hours to cover, right about at 2 hours, but we'll lose the first 10 minutes today from finishing 5.2. So I would advise every one of you to go ahead and start working on that homework for 5.3 to cover the problems that you have seen in lecture by the end of today. And that way it won't be a rush to get everything done next class, next week, whenever it is that you would be working on it. So remember, stay ahead as much as you can. Just because I'm not saying 5.3 isn't due in a week doesn't mean you shouldn't go ahead and start it today, tomorrow, the next day, whenever. All right, so I don't really have too much else to introduce, so let's go ahead and finish 5.2, and then we will go right into 5.3. And as a reminder, if you ever hear me say chapter 7 instead of 5, that's just an issue from us changing textbooks editions and actual textbooks, and chapters being shuffled around and such. So I apologize for that, but remember, we're not doing anything from chapter 7 for quite some time. It's all chapter 5. Again, if you hear me say chapter 7, ignore it. If you ever hear me say a due date that doesn't make sense in the middle of class, ignore it. All our due dates will be said at the beginning and or end of classes. Sometimes it's just I've had these videos from a few months ago or something like that, and maybe I say a date accidentally because I'm not thinking about it. And every now and then I'll make a date in the currently, I'll have some notes with a date on it, and I automatically read it because that's what my brain does. So, all right, let's get it.
We are going to evaluate in a calculator. Okay. We're going to have the sine of 26 degrees. I'll go ahead and write them all up at once since it's just type it in. For B, why did I do it equals? Because I was looking at one. The cosine of 3 pi over 11. Not a very common angle, but that's all right. For C, we're going to do the tangent of 428 degrees. And then for D, we'll do the cosecant of 45 degrees. And I'm going to warn you, in about 8 minutes, I'm going to have to go on mute for probably about 5 minutes total, maybe less. I have something to take care of on a very specific time that I can't avoid. Sorry for that. So I'll let you know, and if I can still type, I will, but I have to be talking to someone else. I'm sorry for that, but it's only going to take a few minutes, I promise. So sine of 26 degrees. Calculator. Let's clear the screen so we don't get any of that confused. Probably should check our mode first. We're in radians. Ooh, that would have been bad, right? So let's switch to degrees, hit enter. Second, quit to get out. Second mode is where quit is. Sine 26. You don't have to type the symbol because of the mode being degrees. It knows this number is a degree because it's inside of a trig function. It's not like if I type 26 or if I type pi that being in degrees or radians is going to change anything. It's when those numbers are inside of trig functions. So the answer is 0.438, and I didn't specify to the number of decimals, so now I'm going to 3 decimal places. So 0.4383, we round down to 0.438. Easy as pie. Pun intended. I know, I'm terrible. Cosine of 3 pi over 11. So if I just do cosine 3 pi over 11, it's going to be wrong because we're in degrees. We got to go back to radians. These problems don't have to be all degrees and then all radians. They can flip-flop like this. Probably why I did it that way. Cosine 3 times pi, so second and then the exponent button, divide by 11. See, I clicked too quick, so the extra 1 didn't show up. Close the parentheses, drum roll, and rounding to the nearest thousandth, that should be 0.655, because the number after that, 4, rounds us up. See, that's an 8, so we round up to the 4 to a 5. These last two are in degrees, so I won't have to check the mode after this, but I do need to switch it back to degrees for now, so I can quit. Tangent of 428, so this has gone a little more than a full circle. It does have an equivalent angle, a coterminal angle, but we're not worried about it. Every angle has a coterminal angle. So we get 2.475, 2.475 when rounded to the nearest thousandth, 2.475. And then cosecant of 45 degrees. Same issue we had up here with trying to do a cosecant of pi over 3 in a calculator. There's no button for it. So we need to change this first. So cosecant of 45 would be the same as 1 over sine of 45 degrees. Okay, so then we can type that into the calculator. We're still in degrees. 1 divided by sine of 45. Close the parentheses. And we get 1.414. And there we go. Right. That is 7.2. Sorry, 5.2. I told you I'm going to say that a few times. I'm still used to this being chapter 7 because it was chapter 7 for me for like 3 or 4 years, if not longer. It's chapter 6 for like a semester. That's 5.2. So we're going to save it. Hopefully Word doesn't crash opening a new file. We're going to go to 5.3. Functions of any angle. Center, enter, spacing, left, give myself some space. If I haven't said, I have to do that at the beginning so that the pen and the text really confuse each other in Word. It's a little silly. And hitting enter sometimes makes text go down. And if I don't do that, it can just break the whole page. Trig functions of any angle. Now, it's kind of funny that I'm going to say of any angle because we're primarily going to study 3 angles and extensions of them. So there are 2 very important triangles to memorize. Trig. Now, some of you may have had a trigonometry class where your teacher was very emphatic about memorizing the unit circle. And I will introduce the unit circle eventually, but you will never hear me say you need to memorize the unit circle. I strongly dislike the unit circle for my type of learning. Remember how I told you the 3 forms of the Pythagorean identities, how I only memorize 1. And I mean, I technically have the 2nd and 3rd memorized in my head at this point, but I still just always do that quick little algebra trick and canceling things to get to them. That's how my mind works. And I think a lot of people's brains work that way and they don't realize it versus just straight up memorization. So we're going to have to know things like the sine of 30, the sine of 45, the sine of 60, the sine of 90, but we're also going to need the sine of 120 and 150 and 180 and all these other angles up to 360 degrees, not just the sines, but the cosines, tangents, etc., etc., etc. So you'll see teachers give this giant unit circle with all these answers, 6 for each angle, and they say memorize it. No. That entire unit circle can be reproduced by memorizing 2 triangles, the quadrantal angles, and then reference angles. That's 3 things that you can put together, 2 of which are extremely simple with practice. One of is just a memorizing of 2, again, very simple triangles, and you can build the whole thing from scratch if you wanted. You don't have to spend 6 hours memorizing just a bunch of data without understanding why it's there. So what are these 2 triangles? The first one is the 45, 45, 90 triangle. And I've already alluded to these in a previous class. So that's 90, 45, 45. So the basic idea here is that if this is 45 degrees and this is 45 degrees, if these angles are equal, the sides have to be equal. So if, let's say, if this length was 20, this length would also have to be 20. But we're going to generalize. Let's make that number as small as possible. What's this and an easy number to use? The smallest easy number to use would be 1. So 1 and 1. That's 1, that's 1. If it's 2, that's 2. But this makes it easier. We can find the hypotenuse by doing the Pythagorean theorem. So we can find this by the Pythagorean theorem. So just really quickly below, if we take 1 squared plus 1 squared and set it equal to, let's initially call it c squared. Each 1 squared is 1, so that's 1 plus 1 c squared, which is 2 equals c squared. So you take the square root of both sides so that they cancel on the right side and just get a c, and you see that c is equal to the square root of 2. That is how we determine that side's length. The next one is going to be, and I'm going to go ahead and draw it up. We'll do the proof after I have this quick discussion with somebody. I'm going to try and do this as best as I can. That's going to erase the whole thing. Yep. I can do better than that. Drawing blind when you are already a bad artist and have terrible handwriting. There we go. So this is the 30, 60, 90. Oops. 30, not to the 6th power, 30 degrees, 60 degrees, 90 degrees. Now for reasons that I'll make you hold your breath on, the side length opposite of 30 degrees we want to be 1. The side length that is opposite the 60 degrees is going to end up being a square root of 3. And this length right here, the hypotenuse, is going to end up being a 2. So this is the 1, 2 square root of 3 versus the 1, 1 square root of 2, or the 30, 60, 90 versus 45, 45, 90. It just depends on how you want to label them. All right, so give me hopefully no more than 5 or 7 minutes. I'll be right back. Sorry for the pause. I wish I didn't have to. All right, so these are your 2 important triangles to memorize. We kind of rationalized how this one works. Like we said, if this is 45 degrees, this has to be 45 degrees because they add a 90. That means the lengths of the legs have to match. The best thing to do in this instance is to make them 1s. And then the Pythagorean theorem showed that that was a square root of 2. I gave you this one. We said we want this to be a 1, the hypotenuse to be a 2, and this other leg to be a square root of 3. Now, what is very specific here is that the 1 is opposite the 30 degrees, and that the square root of 3 is opposite the 60 degrees. There's a relationship here. The bigger the angle, the bigger the side opposite of it. 1 is bigger than square root of 3. I just said that wrong. 1 is smaller than square root of 3, excuse me. 1 is smaller than square root of 3, so it has to be opposite the 30 degrees. Square root of 3 is bigger than 1, so it has to be opposite the 60 degrees. 2 is actually the biggest number, and if you don't trust me, we'll show you what the square root of 3 is. Square root 3, it's 1.7. So that's the middle number. And it might confuse you because you might just think it's a 3. That's square root of 3. So again, smaller angle gets the smaller number. Bigger angle gets the bigger number. The biggest side is the 2, and that's opposite the biggest angle of 90 degrees. I cannot tell you how many students will put the 1 over here and the square root of 3 over here with the 30 and the 60 set up like that. It's wrong. You have to memorize it. You have to practice it. You have to be careful. Now, guess what? Your teacher's made that mistake once or twice in his life because nobody's perfect. But I always try to pay attention to make sure that I wasn't just rushing and I don't make that mistake happen. Okay, so why is this triangle a thing? Where's the proof of that? So down here, I'm going to draw a second triangle. And this is going to be, if I was a better artist, a triangle where all 3 of the angles are the same. So this is my choice. I'm making this triangle happen right now. Now I'm going to make another choice. If all of these angles are the same, that means all of these sides have to be the same. So what I could do is I could say this is 305, that makes this 305, and that makes this 305. But that's a very arbitrarily chosen number, so I'm not going to do it. Now what you might think is, well, you made an arbitrary side 1 before, let's do that again. That's a great idea, but I'm actually going to make it 2. So I'm going to make it a 2 instead of a 1, and I have a reason for that you're going to see in just a hot second. So all these angles match, so all the sides match. It's an equilateral triangle, that's what it's called. So here's what I'm going to do. I'm going to split this sucker in half exactly. And out of that one triangle, I'm going to create 2 triangles. This is why I made these numbers 2s instead of 1s. Because if I made those 2s, when I split this up, then this distance would be a half, and this distance would be a half. Now that's not wrong, it's just a little more annoying. Don't we like whole numbers over fractions? I know I do. So that's why I chose the 2s. I knew to do that ahead of time because it's not the first time I've done it. But if you made these 1s originally, then these would just be halves, and you'd go, oh, well, to avoid that, let me go back and make them 2s. Guess what? Been there, done that. All right, so if I split this perfectly in half, since this was 60 degrees, that means I now have a 30-degree angle here and a 30-degree angle here. This has to be right. And if this whole distance was 2, since we're splitting this exactly in half, that means that the distance from here to here has to be 1. The same for the other side. This distance would have to be 1 from here to here, from here to here. So now what I'm going to do is I'm going to make another triangle, but what I'm going to do is I'm going to extract it from this. So I had the one red triangle that I split in half to make 2 blue triangles, we'll say. Let's ignore the second one. Let's just use the first one. Does it matter which one? No. Let's use the right one. All these were pointed the other way, so let's use the right one. So I'm going to take this one. Again, I'm just taking what's right here, and I'm redrawing it by itself. So this distance was a 2. That hasn't changed. This is still a 2. This distance was half of the original distance across. It's a 1, which means this is an unknown. It's a b for now, which I'll erase in a bit. But you can solve that by, you guessed it, Pythagorean. So we can go 1 squared plus b squared is equal to 2 squared, which is 1 plus b squared equals 4. You can subtract 1 on both sides to get that b squared is equal to 3. So let me move up here. Take the square root of both sides. You're going to be doing this over and over and over throughout the course. And that says that b is the square root of 3. So that is why the 1, 2 square root of 3 triangle, it exists, and I didn't put the angles back in there, where this is 30 degrees, this is 60 degrees, and this is our right angle. That's the proof of this thing right here. That's why that triangle exists. Do you have to memorize this proof? No. Do you have to memorize these two triangles? You could argue no if you're a fan of that giant pain in the butt unit circle. I'm going to suggest that you try my way if you have done trigonometry before and didn't. If you hate it, then rely on the unit circle, but you have to learn one of those two methods or something in the universe that works as well. Okay, so why exactly is it that we have to memorize these? Because remember earlier how I said, oh, we don't know how to find the sine of 26 degrees without a calculator. We don't know how to find the cotangent of 81 degrees without a calculator. We don't know how to do the cosine of 3 pi over 11 without a calculator. You know what? Trigonometry existed before calculators. And people just had these giant, and I mean massive, tables of numbers for trig evaluations. So someone was literally measuring these things out for probably years, creating this table of values, and then you just looked it up. And the ones that are more popular, you probably memorized eventually. But we got calculators, so we don't have to do all of that part. But there's still a lot of them by using the two triangles we just showed that we can actually get analytic answers without ever using a calculator. Because with 30 degrees, 60 degrees, 45 degrees, we can create right triangles out of them, and then we can use opposites, adjacents, and hypotenuses, hypoteni, to get their trig function evaluations. There's no nice fancy right triangle for the 22-degree angle or the 37-degree angle. There's only maybe one more good one of these in existence, and I'm not even going to introduce that in here because we won't ever use it, in fact. So these are critical for what we're about to do. Draw them 50 times, write them 50 times, say them 50 times, have someone else say them 50 times to you, however it is you learn. So now what we're going to do is we're going to establish, let's go off of my ridiculous font from my BRB. And again, thank you for your patience. I'm sorry I had to do that. But sometimes phone calls are phone calls. They can't be rescheduled. So let's discover what the basic trig function evaluations are for common angles. 30, 45, and 60 degrees. So for the sine of 45 degrees, we'll do the 45 first. Sine of 45 degrees. Now remember, SOHCAHTOA. Remember, we have the 1, 1 square root of 2 triangle for the 45, 45, 90. And then we have the 1, 2 square root of 3 triangle for the 30, 60, 90 triangle. Remember, 1 opposite the 30. That's critical. 2 is the hypotenuse there. 2 is the hypotenuse for both of these, but one of them is a radical, one of them is not. So sine of 45 degrees, that's SOH, S-O-H, opposite over hypotenuse. So the opposite over the hypotenuse, first of all, since it's 45 degrees, we're using this triangle. That's where our eye should be. And it's going to be easiest if we refer to ourselves from this bottom left angle, even though it's the same. You'll get the same answer. So from this one, this would be the opposite, this would be the adjacent, and this would be the hypotenuse. So sine is opposite over hypotenuse, so that's 1, this 1, over square root of 2. Now, this is a problem that we discussed last class. You don't get to have radicals in your answers. This is not acceptable. You have to rationalize the denominator, and that technique was to multiply top and bottom when it's a monomial by the square root in the bottom. If these are cube roots, the technique is different, but we don't really have that as an issue in here. So 1 times square root of 2 in the top is square root of 2. In the bottom, square root of 2 times square root of 2 is square root of 4. But the square root of 4 is 2. That's why we did this. We need this bottom to be a non-radical. It has to be a whole number. So the sine of 45 degrees is the square root of 2 over 2. Sometimes it's important to understand that it's also 1 over square root of 2. In fact, that's generally how I do it. And in fact, I don't memorize this at all. Like I said, I use this triangle. But if you were going to memorize it, understand that the memorization is 2 versions of it. You could memorize this one or this one. If you're memorizing this one, you got to clean it up. Again, this is us avoiding memorizing a unit circle. So the cosine of 45 degrees. Again, we're still here. Now we're going to do the adjacent over the hypotenuse. We're on CAH, C-A-H. This is the adjacent if we're using this as an angle. And that flip-flops if we use the other one. So adjacent over hypotenuse, that's 1 over square root of 2, which, guess what, is the exact same thing as before. So the work will be the exact same. I'm not going to reinvent the wheel. You do if you need to. Then let's do the tangent of 45. So again, using this triangle, TOA. Tangent is the opposite over the adjacent. The opposite is 1, the adjacent is 1, so that's going to be 1 over 1, which is 1. Like I said, some students memorize these, some students take my advice and use the triangles and SOHCAHTOA to put this together as a puzzle instead of just blatant memorization. Blatant memorization is great for classes like anatomy, but even still, if you know Latin, there's a lot tied in there. It's not just memorization anymore. It's actually, you can put some logic to some bones and things like that, which that's not my expertise, so I'm not going to pretend like it is. I just know those 2 little facts. All right, so there's our 45s. Let's go to the 30s. So the sine and cosine and tangent of 30 degrees. So we're on this triangle that I drew a little sloppy, but that's okay. You're not going to judge me for that, I hope. So 30 degrees, here's our angle, which makes the 1 the opposite, the square root of 3 the adjacent, and the 2 the hypotenuse. Again, I don't like that stuff being staying there permanently. You can do it that way in your notes, but not in mine. So sine of 30, SOHCAHTOA, S-O-H, opposite over hypotenuse. So the sine of 30 degrees is the opposite, which is 1, over the hypotenuse, which is 2. Awesomely enough, there's nothing else to do. The sine of 30 degrees is exactly a half, or 0.5 if you like decimals. So they're not all ugly radical numbers. These 2 are radicals, but the tangent of 45 was 1. The sine of 30 is a half. And don't just play a guessing game with this. And to figure out, hey, do I think it's going to be a radical or not? Do the work. Cosine of, I'm looking at the 45, sorry for that. Cosine of 30 degrees. So again, back to our 30, 60, 90 triangle. We're here, opposite adjacent hypotenuse. So the adjacent's the square root of 3. We're on CAH. Adjacent over hypotenuse, square root of 3 over 2. So this would be the square root of 3 over 2. That's it. You don't have to clean this up because the bottom number is not a radical. This is perfect. It's fine. How about the tangent of 30 degrees? So going back up to our triangle. 1, 2, square root of 3. Again, 1 is the opposite, square root of 3 is the adjacent, 2 is the hypotenuse. Tangent of 30 degrees. Tangent is TOA, opposite over adjacent. The opposite is the 1, the adjacent's the square root of 3. So that's going to be 1 over square root of 3. That one does have a square root in the bottom, so we got to multiply top and bottom by square root of 3 over 3. Square root of 3 over square root of 3. Which will give us the square root of 3 over the square root of 9, which is the square root of 3 over 3. And that's the answer. Now let's switch to the 60-degree angles. So the sine of 60. And I'm going to redraw them here for reasons. 45, 45, 90, degrees, 1, 1, square root of 2. When I'm starting out, I really like the angle I'm referencing to be this one. You can certainly do it from here. So from this, when you're talking about 60 degrees, the square root of 3 is the opposite. That's not a 0, that's an O. The 1 is the adjacent and the 2 is the hypotenuse. See, it's not that the adjacent's always the bottom, it depends on what angle you're referencing from. So me personally, I know a lot of students mess up when they reference this way. So I'm going to redraw that thing. I'm going to redraw it with 60 degrees being that kind of anchor angle. So that's the wider one. Let's make it look something like that. So this will be our 60 degrees, which makes this the 30 degrees. There's our right angle. 30 degrees is supposed to be opposite the smallest number, which is 1. 60 degrees gets the square root of 3. 2 is opposite 90. Again, those are the largest numbers. So now the sine of 60 degrees, sine opposite over hypotenuse, opposite square root of 3, hypotenuse is 2. Square root of 3 over 2, and that's it. If I did it up here, I would have gone opposite of square root of 3 over 2. It would be the exact same thing. Notice something. Notice that this answer, the sine of 60 degrees, is the same as the cosine. I hate scrolling when I'm on draw. Is the same as the cosine of 30 degrees because they're cofunctions. 90 minus 30 is 60. They have the same answer. That right there helps show that cofunctions isn't just nonsense. All right, so the cosine of 60 degrees. So here, adjacent is 1, hypotenuse is 2. So the cosine of 60 is a half. The same thing as the sine of 30. 60 versus 30, those are cofunction angles. Sine versus cosine are cofunctions. Finally, we have the tangent of 60 degrees. Tangent is TOA, SOHCAHTOA, T-O-A, opposite over adjacent, square root of 3 over 1, which we do not need to clean up in terms of rationalization, but we do need to just write that not as a fraction for simplicity. You are going to do these 9 evaluations literally hundreds of times in this course. There is no exaggeration in my voice at all here. I use the word literally, not like from Parks and Rec. Sorry, silly there. But anyways, you will literally do these hundreds of times. That is not a joke. That is not exaggeration on the word. Or what's the fancy way of saying that? I'm not being hyperbolic, which we'll actually study hyperbolas later, which are not hyperbolic discussions. I have too much fun. Do this, then do it again, then do it again, then do it again, then do it again. Draw these triangles 50 times. Do these 9 evaluations 50 times. Whatever it is you have to do to get it stuck in your brain and ready to use over and over and over. And again, sure, you can blatantly memorize that sine of 45 is square root of 2 over 2. I never did it that way. I did exactly what you just saw me do. I took a triangle that has the information that I can extract for SOHCAHTOA, and then I did a rationalization because you have to. Not all of them have that rationalization. I only actually did it 2 times. Well, 3 if you argue about this one, but I shortcut it. Know which triangle you're supposed to use. Set the triangles up correctly. You're going to be mad at yourself on a test if you draw up these 2 triangles, but you swap the 30 and the 60, or you swap the 1 and the square root of 3. Every semester, I'm going to say at least 1 student, but it's a lot of students that do that. And maybe not for every problem, maybe just for some. So it's learn consistency, practice. Remember, how much time do I get out of you for homework every week? At least 6 hours. And Monday's a holiday, so you're probably going to be doing trigonometry for 8 or 10 hours that day, right? Right? Haha. Okay. Where am I going with this? Where am I going with this? Remember the title of this section was trig functions of any angle. Well, those were just 3 angles. What about if we were in quadrant 2, 3, or 4? So we can kind of open this up to any angle. Any angle outside of quadrant 1. We want to use something known as a reference angle. Evaluate trig functions. What is a reference angle? I'm glad you asked. The reference angle, angle from the closest. I'm going to all caps that and underline it actually, or bold it. Let's bold it in all caps it. Closest x-axis, terminal side of your angle. So we said that when we're talking about angles, our initial side is supposed to be the positive x-axis, and the terminal side is wherever that angle forces us to be. And we drew up dozens and dozens of those in previous classes. But in order to use that 30, 60, 90 or 45, 45, 90 triangle when we're outside of a quadrant, outside of quadrant 1, I mean, what we can do is use a reference angle. We can actually turn something like 120 degrees into 60 degrees as a reference angle. Or we could turn 91 degrees into 89 degrees as a reference angle. And there are reasons for this that we're going to study over the next couple of classes. I don't want to give you too much of a kind of a proof for this for now. So let's take a little leap of faith with me, and we'll start seeing why this actually works over time. All of the trig functions, again, leap of faith for now, all of the trig functions be identical for the original angle and its reference angle, which looks like this. You still have the same theta, but you give it a little 1 as an exponent. It's not actually a 1, it's not actually an exponent, it's just notation. So when you see that, it's known as a prime. So that's called theta prime. That's a reference angle. That's the terminology and notation that we use for a reference angle. So an angle and its reference angle will have the exact same trig function outputs, except for a potential sign, SIGN sign change. So for any angle outside of quadrant 1, we are going to want to use a reference angle. If you're not just going to blatantly memorize a unit circle, we're going to want to use a reference angle. So we're going to take an angle that was in quadrant, say, 3, and make a reference angle that would go in quadrant 1. Because when we're in quadrant 3, we can't really make a right triangle out of the angle from the positive x-axis. So we want to be able to create a right triangle, which means we're stuck to less than 90 degrees. But the beauty is, besides maybe a change in the plus or minus sign of the answer, the sign of a regular angle, SIN, sign, will be the same thing as the sign of its reference angle, except maybe negative. The tangent of an angle will be the same as the tangent of its reference angle, except maybe negative. The cosecant of an angle will be the same as the cosecant of the reference angle, except maybe plus or minus difference. So here's kind of the idea here. If we have a regular Cartesian coordinate system, here's our x-axis, here's our y-axis, and I'm going to draw in the first quadrant for this one, but let's say that our angle formed is right here. Here's our terminal side. Now this point we'll call P. It has coordinates x and y. So here's our traditional angle. And let me just kind of form a right triangle out of this. So even though the angle itself doesn't say make a right triangle, this is what we like to do. We like to form a little right triangle out of it, like so. So if that coordinate is x comma y, the distance along the horizontal part is that x value, and the distance along the vertical part has to be the y value, because you have to go right and up, right based on the x number, up based on the y number. So for this angle, if that's your angle, the opposite is y, the adjacent is x, and then the hypotenuse because we're generally going to talk about this thing in relation to a circle, we label as the letter R. So that your 6 trig functions are just the sine of theta would be the y value over the radius. The cosine of the angle would be the x value of the radius. The tangent of the value would be opposite over adjacent y over x. See, I'm just giving these different names. Instead of calling them opposite, adjacent, hypotenuse, I'm giving them names that are related to their points, x, y, and r. Or we can do the other 3. Cosecant would be r over y, just flipping the sign. Secant would be flipping the cosine, which is r over x. And then cotangent would be x over y. So this is going to be important, especially for what we call the quadrantal angles. But it also helps us establish this whole everything's the same for an angle versus reference angle, except maybe a plus or minus aspect and sign change. So now I'm going to draw this thing not being in quadrant 1. So that was just to establish the blue stuff over there. Now let's do an angle that's over here. So here's our theta. Here's the lengths if we want to make a right triangle out of this. This length would be our opposite. This length would be our adjacent. For the point itself, this point right here, let's give it, instead of giving it x and y, let's call it a and b. And hold on, I need a little more cleanliness there. A and b, and I need a little more space too. A comma b, because I'm going to change something about this in just a second. So this point right here, if I call that a and b, that means that this height is a, which means this distance is a. Incorrect. Sorry, I'm rushing in my head. Not rushing, but I'm moving ahead in my head. That's not the a. If that height, that's the height, that's the b. That value should be b. And then initially, I'm going to call this over here a, but that feels weird to call it a because it's negative. Now, it's fine. We could just say, okay, a could be positive or negative. But I want to have this labeled as a as well. So let's instead make this a negative a. Do we see why I'm calling that a negative and then b a positive? But I'm doing that so that I can just label these sides as a and b. So in the right triangle, there's no positives or negatives. But in terms of actual coordinates, because we're going left, that makes this a negative value. So this point right here is negative a comma b. So here is the, I'm sorry, where I put theta, I'm also doing that wrong. That wasn't theta. This is the theta. The actual angle is swinging over here. Inside, this would be our reference angle theta prime. So I'm going to do this with red so it screams out. So that's our reference angle. A reference angle is us taking an original angle and making it something inside of a right triangle, something less than 90. And spoiler alert, it's going to end up typically looking like this when you draw it out. And we'll talk about how to mathematically calculate these after. Okay, so if this is your regular angle, so we're going more than 90 degrees, maybe 120 degrees, maybe 132 degrees, something like that. This angle would have to be its supplement to make sure that they form a straight line. We discussed that last class, that 2 supplemental angles add to 180. So if this was 120, that would make this other one 60 because 180 minus 120 would be 60 degrees. So let's take this triangle and let's draw it again. And I'm going to do it with orange to make it scream out. But I'm going to draw out the reference triangle with the reference angle in quadrant 1. That's a little too steep, or actually not steep enough technically. I'm trying to do as best as I can here. So now this little angle right here is going to be theta prime. And it's going to have sides over here and here. Now, these are very, very symmetric. Symmetry is the name of the game. So if this vertical distance is b, this vertical distance is b. If this horizontal distance is a, this horizontal distance is a. It's basically just reflecting it across the y-axis. When you reflect something across a y-axis, the point just changes in x value. So the point is now a comma b. And it is this idea that makes all of those trig functions the same, except in terms of SIGN sign. Because the right triangles I just drew up mimic each other, it's just for the original one, that was supposed to be a negative for the x value. Over here, it's a positive. So if you use this version of it, you just got to remember to put a negative in the answer when you were in quadrant 2 or 3 or 4, depending on the trig function. So I just threw a lot at you that probably doesn't make a lot of sense at first, but after we do this 100 times, it starts to really sink in after you see these evaluations come through. But again, the main point of this little drawing detail was to say, all trig functions will be identical for an angle and its reference angle, except for a potential sign change, and that's because of these coordinates basically changing SIGN sometimes. And these coordinates tie in to the sine, cosine, tangent, secant, cosecant, and cotangents. So if a coordinate changes sign, that means its trig function changes sign. So let's give you a mnemonic device to help you. A, S, T, C. This stands for a smart trig class, which is what we have right here. Kind of like FOIL, in that FOIL helps us remember first, outer, inner, last for multiplying binomials together. It's kind of like PEMDAS, please excuse my dear Aunt Sally, to remember the order of operations. It's kind of like SOHCAHTOA, some old horse got another horse taking notes away, to help us remember sine is opposite over hypotenuse, etc., etc. So what does this really stand for? All sine, S-I-N, tan, and then cosine. That's what it stands for. All sine, tan, cosine. What this does for us, this describes which trig functions out of the three primary, sine, cosine, and tangent, are positive in which quadrant. So in quadrant 1, they're all positive. Quadrant 2, it's only the sine that's positive. Quadrant 3, it's only the tangent that's positive. Quadrant 4, it's only the cosine that's positive. I'll abbreviate positive. Notice I switched from Roman numerals to regular old numbers. I actually did that on purpose because I don't care. In my math lab, they will probably specify which one you'll need to answer, but it's very rare you're answering a quadrant as part of a homework question. Why exactly is this? Let's draw up another one of these. And I'm going to label in each quadrant the sign, the positive or negative sign of the x coordinate, the y coordinate, and the ratio of the two. But specifically y over x because that's going to relate to tangent. All right, so if you're in quadrant 1, an x coordinate has to be positive. If you're in quadrant 1, a y-coordinate has to be positive because you go right or up or right and up. And the division of a positive and a positive is a positive. If you're in quadrant 2, your x is negative because you've got to go left, but you're still going up, so your y is positive. And if you divide a positive and a negative, you get a negative. In quadrant 3, you're going left and down, so your x and y coordinates are both negative. However, the ratio of them is positive. If you're in quadrant 4, you're going right and down, which means your x is positive because you're going right. Your y is negative because you're going down, and the ratio of them would be negative. A negative divided by positive is a negative. Why did I do this? I'll come back to it in a second. Because all of your sines and cosines and tangents are essentially based on the x's and the y's. You might say, well, Mr. Beckner, you didn't talk about the r's. R is the radius of a circle. It's always positive. We're not considering a coordinate for the radius. That's just an intrinsic value. So x divided by r is positive, it won't be affected. Y divided by r, it's not affected because it's positive. So since sine essentially goes like x, this is like a tilde, a curly equal sign, but only one of them. This says sine goes like y. I wrote x because I was looking at an x. I keep doing things like that today, I'm sorry. Sine is essentially the y coordinate. It picks up the plus or minus aspect of the y coordinate. Cosine picks up the plus or minus aspect of the x coordinate. Tangent was opposite over adjacent. Opposite over adjacent is y over x. So tangent picks up the plus or minus aspect of the ratio of those two. So because when you go right, x is positive, that says your sine is positive in quadrant 1, and it's positive in quadrant 4. But to go left, that makes it negative, so your sine is negative in quadrant 2 and in quadrant 3. Your y value is whether you're going up or down. You're going up in quadrant 1 and 2, so you're I keep doing that. I keep saying sine instead of cosine. X's are cosines. And I know why. It's because I usually write y and then x on this. That's what screwed me up here. X goes like cosine. See, x goes like cosine. That was my bad. So cosine positive, cosine negative, cosine negative, cosine positive. Y's are heavily related to the sine, the SIN. So we're going up, positive. We're going up, positive. We're going down, negative, down, negative. Left and right is cosine or x. Up and down is sine or y. Tangent is the ratio of the two. Everything I filled out is right here in ASTC. All of them are positive in quadrant 1. So here's your all. Here's your A. All. There's your all. They're all positive. Why did that get weird? They're all positive in quadrant 1. In quadrant 2, it is only the sine that is positive. Look at that. Cosine and tangent are negative. Sine is positive. So it's only the sine that's positive. In quadrant 3, it's tangent that's positive only. Negative, negative, yep, tangent's positive. And in quadrant 4, it's cosine is the only one that's positive. And sure enough, cosine's the only one that's positive. So here's what you can do as students. You can recreate this, and you don't have to do it with as much detail. Remember that sine goes like y, cosine goes like x, tangent goes like y over x. Spoilers, you will need to memorize this ultimately anyways. This will keep coming back to haunt us. But if you don't just want to blatantly memorize or have to recreate this diagram every time to remember in which quadrant sine's positive and which quadrant it's negative, that kind of thing, this ASTC gets all of that a lot quicker. So you know if your angle is in quadrant 2, if you're doing a sine, it's going to be positive. If you're doing a cosine, it's going to be negative. If you're doing a tangent, it's going to be a negative. But Mr. Beckner, what about the other 3 trig functions? What about secant, cosecant, and cotangent? How do I know whether they're plus or minuses? because reciprocal relationships share the same plus or minus. So if the sine is positive, that means the cosecant is positive. If the cotangent's negative, that means the tangent's negative. They go hand in hand. So for cosecant, secant, and cotangent, just use reciprocal identities. Plus or minus aspects. Same for recips. And unfortunately, on that bombshell, we're going to have to cut class because it
Ignore that remark, obviously.
is time. This is what I was just referring to, the little board cheat sheet. Thank you for catching that. Okay, so very quickly starting fresh. Hi everyone, this is what I was just referring to, the little board cheat sheet, which again, sometimes I'll have extra things on here, sometimes I won't, sometimes might have less of this up here. It's more about what's relevant for the day, and we won't use all of it necessarily. But your SOHCAHTOA, your reciprocal trig functions, let me not say inverse, that would have been wrong. Your Pythagorean identities, your 45-45-90 triangle, your 30-60-90 triangle, a couple of quick radian to degrees conversions that we see constantly just to get used to. And this is something I won't write anymore after a week or two. Then the last thing that we did, which was developing how to find the trig function of an angle outside of the first quadrant, so no longer restricted to a right triangle. Because we said that we use these reference angles and then it just might have a negative half the time. And it turns out that the patterns, based on the fact that sine goes like y over the radius, cosine x over the radius, and tangent the ratio of y over x, because that would be sine over cosine, that all of these are positive in quadrant 1 because all of the x and y coordinates are positive. Sine is the only positive one in quadrant 2 because you're going up and sine relates to y. Tangent's the only thing that's positive in quadrant 3 because sine and cosine were both negative and that ratio would be positive. And then cosine is the only thing positive in quadrant 4 because you're going right and down. So a smart trig class helps you remember they're all positive in quadrant 1. Sine's positive in quadrant 2. Tangent's positive in quadrant 3. Cosine's positive in quadrant 4. Remember, I don't care how you're going about memorizing and using things. I just care that you have a system that works for you, that is legitimate. So that's why I've given you both of those versions. And then the last thing that I want to do before actually continuing into 7.3, you don't need to see my virus notifications. Before we continue into 7.3, I believe this actually goes back to, and I said 7, I meant 5. I told you I'm going to keep doing that. 5.1? Yeah, it's 5.1. Oh, just not over my notes. So converting between normal degrees and then a degrees, minutes, seconds system. So this is just going to be something that you'll see in the homework, not on the test, but it's something that you could come across in another class that involves trigonometry. So I still want to make sure you have this methodology, but it's converting between decimal degrees and degrees, minutes, seconds. The idea is all about multiplying or dividing by 60. That's all it is. So if you're starting in degrees with decimals, So something like 3.5 degrees. What you will do is to get the minutes and the seconds, multiply the decimal value by 60 to get the minutes. Then, if this number has a decimal, multiply it by 60, get the seconds. That's it. That's all it is. So if you're starting in decimal degrees, something like 1.52. So 1.52 is what I'm starting with. What you do is you take the decimal value of 0.52. So 0.52, and you multiply it by 60. That gives you your minutes because there's 60 minutes in an hour. So the degrees are kind of like your hours. So 31.2 is the minutes, but we're trying to avoid decimals. So now we take this decimal value. So 31 will be the real minutes, but the 0.2 will give us our seconds. So now what we have, let's see if I can just do this. So we had 1.52 degrees. We multiplied the 0.52 by 60 to get 31.2 minutes. But then we take the 0.2 and multiply it by 60. And that'll give us 12. So that means it's 12 seconds. So that means this is really 1 degree, 31 minutes, and 12 seconds. Going the other way, starting in DMS, degrees, minutes, seconds, take the seconds and divide by 60. We're just doing the opposite, basically. And add this to the minutes and divide by 60. So let's work backwards. Let's take the 1 degree, 31 minutes, 12 seconds. Let's take the 12 and divide it by 60. And we get 0.2. 12 divided by the 60 is 0.2. Add this to the minutes. So 31.2, then we're going to divide that by 60. 31.2 divided by 60, and you get 0.52. That's your decimal. So the original number, 1D, 31 minute, 12 seconds, would be 1.52. The same thing we originally had. And that's degrees, of course. This is not something you will ever see me do in class again. But there are certain schools of thought, if you will, that prefer degrees, minutes, seconds over just a decimal value for degrees in general. So they'll go and do that conversion. Maybe if you're an engineer and you want just a little more specific accuracy, it doesn't really make it more accurate technically, but it just might make it more relatively accurate to their own system. So again, you'll see 1 or 2 of these in the homework. You're not going to see it on the test. It's not something you have to master, but I still wanted to introduce it because you might come across it at some other point, and at least you've seen it at one point in your life. All right. So that's our degrees, minutes, seconds. Oops, wrong button. So here's our board, our whiteboard that we'll pop back over to every now and then. But for now, let's go back to 5.3. So again, the last thing we developed in 5.3 was a smart trig class talking about the SIGN pattern of your 3 main trig functions in the specific quadrants 1, 2, 3, and 4. We developed this because any point in quadrant 2, 3, or 4 can be made a relative point in quadrant 1 just by changing the signs of their x and y coordinates. So a reference angle, the theta prime, can always be found based off of an original angle, and their two trig functions are the same except maybe a negative of one versus the other. And we're going to go over how to figure out what the reference angles are and how to use them coming up. All right, so example 1. If the sine of theta, I'm going to write the theta in just a moment, is greater than 0, the cosine of theta is less than 0, which quadrant must theta be in? So if the sine of your angle is positive and the cosine of your angle is negative, which quadrant must the angle be in? So we're going to learn how to tell this. Now you have to be given two conditions. You cannot tell the quadrant just based on one, because if I just tell you sine's positive, well, sine's positive in quadrant 2 and in quadrant 1. So you could not tell me which quadrant it would have to be in. You could say it's in 1 or 2, but I'm not sure. So that first condition, if sine of theta is positive, that says we have to be in quadrant 1 or in quadrant 2. And again, the reasoning behind it is sine is tied to y. Essentially, y is going up in quadrants 1 and 2, which makes it positive. So the first condition says it's in quadrant 1 or 2. We're not sure yet. Second condition says, all right, the cosine has to be negative. Cosine's tied to the x value, and we want the cosine to be negative. X's are negative when you go left. So cosine's negative in quadrant 2, and cosine's negative in quadrant 3. Now I'm doing the rationalization using the coordinates x and y, but you also could just do this all based on a smart trig class. You can draw this up all by using ASTC. I even did it a little more color-coded on the cheat version of the board. Wrong thing. See, I color-coded it. The positives are blue. All, sine, tangent, cosine. A smart trig class. Then that just makes the rest negative. So the second condition, cosine is negative, says we were in quadrant 2 or in quadrant 3. Well, you just got to make it happen in both. So the first condition says we're in quadrant 1 or 2. The second condition says we're in quadrant 2 or 3. Take the overlapping one. Thus, theta in quadrant 2. That's it. You just got to make sure both conditions are upheld. It can't be in quadrant 1 because the second condition fails. It can't be in quadrant 3 because the first condition fails. And that was example 1A. I forgot my A. A. B, if I hit enter, it'll screw everything up. Sorry for that. Oh, that's too low. B. Right. If the sine of theta is less than 0 and the tangent of theta is less than 0, which quadrant are we in? So if the sine of theta is negative and the tangent of theta is negative, what quadrant are we in? So these are the two conditions. Condition 1 says, well, the sine has to be negative. Sine goes like y. So whenever the y's are negative, when the y's are going down, we're going down on this. So down puts us in quadrant 3 or 4, and this confirms it. Sine is negative in quadrant 3. Sine is negative in quadrant 4. Each of these are split 50-50. So quadrant 3 and 4. So by condition 1, it's quadrant 3 or quadrant 4. But the second condition, I didn't mean to switch my numbering that time. The second condition was that the tangent has to be negative. So we can go back up to this. Where's tangent negative? Tangent's negative wherever the ratio of your coordinates is negative. Or you can use a smart trig class. So tangent's positive in quadrant 1. It's negative in quadrant 2. Oh, there's one of them, so quadrant 2. It's positive in quadrant 3, so that's out. And it's negative in quadrant 4. So we're either in quadrant 2 or we're in quadrant 4. So the second condition says we're in quadrant 2 or quadrant 4. What's the overlap? Quadrant 4. Thus, your angle, theta, in quadrant 4. We're not finding any sines or cosines or tangents of these larger angles yet. We're not up to that point. We're getting close. We're getting very close, but we're not there yet. All right. Let's try out something kind of similar, but let's beef it up a little bit. Example 3, excuse me. And for A, given that the sine of your angle is equal to -3/7, and the cosine of the angle is negative, let's find tangent, the angle. Remember that second section, excuse me, 5.2, we were restricted to a right triangle. We were restricted to angles between 0 and 90 degrees. We only established sines, cosines, and tangents for 30 degrees, 45 degrees, and 60 degrees. Yes, they exist for all sorts of other angles in between. We didn't establish them. Now we are in the whole entire 360 degrees or 2 pi full circle, any quadrant, not just quadrant 1 from 0 to 90 degrees. We're thinking quadrants 1, 2, 3, or 4. So the sine of the angle is -3/7. This ratio of 3 to 7 is going to help us find the third missing side if we were to call this a right triangle. And then we'll be doing a tangent of that. But because we can be in any quadrant potentially, we now need to know whether these things are positive or negative, and we have to have two SIGN sign conditions to be able to pinpoint that. Without this second condition, if the sign is negative, that means we're going down, that means we're in quadrant 3 or 4. But you can't tell me the tangent of it because you don't know if you're in 3 or 4. The answer could be positive something or negative something. It depends on whether you're in quadrant 3 or 4. So that's why we needed the second condition that I temporarily scribbled out. All right, so if you draw up a reference triangle, first, it will look like this. So this is not going to be the angle, this would be the reference angle. So this will be theta prime. Now the sine is -3/7. Sine is SOHCAHTOA, S-O-H. So that's opposite over hypotenuse. So the opposite is supposed to be the 3. Now I'm drawing this as a right triangle, so writing it as a negative might throw you off. So I'm going to do it as a positive. It's up to you if you write the negative. It won't matter ultimately, but let's just see what happens. And then the hypotenuse is supposed to be 7, which means we can find this side if I label it as A by Pythagorean. We can say that A squared plus 3 squared is equal to 7 squared. Or A squared plus 9 is equal to 49. So going down here, that says that A squared is equal to 40 if you subtract 9 on both sides. And then when you take the square root of both sides, you'll get the square root of a squared is equal to the square root of 40. But we can simplify the square root of 40. So we get a equals the square root of 40. But we can break up 40 as a product, 4 times 10, because we know the square root of 4. You wouldn't want to do 2 and 20 because you don't know either of those square roots. Whoops, sorry for that erasing. This pen is wacky sometimes, which gives us 2 square root of 10. The square root of 4 is 2, so that popped out. The square root of 10 stays. So that's the A. That is the adjacent side to the reference angle. Now that we have A, which is the adjacent, we could be able to find tangent with one extra feature. Tangent's supposed to be the opposite over the adjacent, so it would be the 3 over the 2 square root of 10, but maybe it's positive, maybe it's negative. It depends on the quadrant. So we said the sign was negative. Since the sign is negative, we're in quadrants 3 or 4. The same statement we said before based on a smart trig class. If the sign's negative, you have to be in quadrant 3 or 4 because you're going down. So that's what the first statement says, in addition to saying that the ratio of the opposite and hypotenuse is 3 to 7. It also says we have to be in either quadrant 3 or 4. But they also told us that the cosine of whatever angle we're finding or dealing with is negative. Cosine being negative means, let's just do the colon, we are in quadrant. So cosine relates to x. X is negative when we go left, and you go left, you hit quadrant 2 or 3. And again, I'm doing the rationalization based on the x and y coordinates of going left, right, up, or down, but a smart trig class finds all of that out for you as well. Pick your poison. So cosine being negative says we have to be in quadrant 2 or 3. What's the overlap? Quadrant 3 or 4, quadrant 2 or 3. Thus, angle is in quadrant 3. So these 3 typed out sentences, statements, whatever, are what we were doing in example 2. But now we've thrown example 2 into the mix, and we're actually trying to find a trig function of said angle. So we know we're in quadrant 3, and we're finding a tangent. We're trying to find the tangent of that angle. Quadrant 3, tangent, a smart trig class, t, positive. So tangent's positive in quadrant 3. So when we do the ratio of our opposites, adjacents, hypotenuses, whatever it is we need, we just got to make sure the answer is positive and we're good to go. That's why I don't really traditionally label these as positives and negatives in these right triangles. First of all, it's kind of misleading because in geometry we can't have negative sides. But I also understand if you were drawing this triangle in its relative position that you'd have a -3 because it'd be pointing down. Also, the A ultimately would have been negative as well because we'd be pointing left. So again, this A is for the reference triangle, not the actual coordinate. It would be -2 square root of 10 because we're going left and down to get in quadrant 3. See here, our angle has to be in quadrant 3. This right here is our theta, which means we're going left and down. So if you drew that reference triangle in there, it would look like this. -3, that's the vertical distance. -2 square root of 10, that's the horizontal distance. And then 7 was the radius, if you will. And then this right here would be your theta prime. Sorry, that's a little small. I'll zoom in for a second. More in a second. Again, this is drawing the reference triangle in its relative position to the original angle. So now the terminal side is exactly where it would have been before. But you don't have to do things that way. Again, I'm showing you alternate ways of doing things because some people like to do them alternate ways. Okay, so finally, the tangent of theta. That's going to be its opposite over its adjacent, where the opposite was the 3, the adjacent was the 2 squared of 10. Now we know tangent's positive in quadrant 3, so this is definitely a positive. If we were in quadrant 2, let's say that for some reason we were in quadrant 2, all I got to do is just make sure I slap a negative on this. Now, if you are doing it this way, all of the signs are correctly in place and you would see the negatives cancel to get this, but I just find that most students don't, or they miss a negative somewhere. So I do think that it's important to understand this as a whole. And unfortunately, this is not an acceptable answer. You have to rationalize the denominator. So you don't have to multiply by the 2, just the square root of 10. You only multiply by the radical part. So you get 3 square root of 10 in the top, over 2 square roots of 100 in the bottom. But the square root of 100 is 10. So that's 3 square root of 10 over 2 times 10. 2 times 10 is 20. So 3 square root of 10 over 20 is our answer. That is the tangent of the angle. I know that seems like a lot to balance all at once, but you will be doing these over and over and over and over and over. This is not going to go away as long as we're doing trigonometry in this class. Did it matter that I set up the reference triangle first and then talk about the sine SIG ends? No, I could have talked about the SIG ends first and then done the reference triangle. The order of these two ideas doesn't matter. You just have to do them both so that you can actually get to this. And again, we made sure this was positive because we're in quadrant 3, so the tangent would have been positive. Let's say, for example, the problem asked me to do the secant of the angle. I'd have to say, well, secant and cosine share the same sign, so it would be negative because we're in quadrant 3. Cosine's negative in quadrant 3, so its secant would be negative. So then I'd have a negative, and then the ratio of opposites, adjacents, hypotenuses, whatever it is. So very common type of problem. That was that little memo for myself reminding me to do DMS last time. Let's try another. So B. Given that the sine, as much as I can for now, back out one layer, there we go. Given that the sine of the angle is equal to negative 2 over square root of 11, I'm just going to write the rest. It's tedious otherwise, and the tangent of the angle is negative. And I don't have to write it this way. I could spell out tangent is negative. Find the cosine of the angle. So this is what we're ultimately trying to do. We're trying to find the cosine of the angle. We're not finding the angle. We did not find the angle in example A. We're not finding it in B. It's actually quite difficult to do that way. My 2 up here looks a little silly, so I'm going to fix that. There we go. All right, so last time I drew the reference triangle first. Let's do the sine issue first this time, the plus or minus sign aspect. Also, you might be saying, Mr. Beckner, you left a square root in a denominator. How dare you? I did that for your benefit because we haven't seen enough of these yet to kind of know what things will look like when the square root's in the top and not the bottom, but we'll get that habit ultimately. So for now, I'm actually doing you a favor right now. So this time we'll do the reference triangle last. Let's go ahead and discuss all of the, why is it not letting me click anywhere lower? That is weird. Word, you're weird sometimes. Okay, so let's do the quadrants. This says sine is negative. So since sin is negative, that means we're in quadrant 3 or 4. Sine goes like the y value of a point. They're negative when you go down. Going down means you're in quadrant 3 or 4. Tangent being negative means we're in quadrant. Let's see, tangent's negative in quadrants. It's positive in quadrant 1 because they're all positive. It's in quadrant 3, a smart trig class, T's quadrant 3. So that means if it's positive in quadrants 1 and 3, it's negative in quadrants, you guessed it, 2 and 4, or 4. And or the wording doesn't matter. Thus, our angle is in quadrant. What's the overlap? 4. To the side, I'll do our reference triangle. Reference triangle, let's abbreviate that out. So the sine is opposite over hypotenuse. So the opposite is 2. The hypotenuse would be a square root of 11. So it doesn't matter what direction you draw your reference triangle unless you're actually putting it in quadrant 4, in which case you'd be pointing this down, but that's not what I'm doing. So here's our reference angle. This is not the legit angle, that's the reference angle, with an opposite of 2, ignoring the pluses and minuses, and a hypotenuse of square root of 11. This makes the third side, A, easier to find by Pythagorean. So we would say a squared plus 2 squared is equal to the square root of 11 squared, which is a squared plus 4 is equal to 11. Subtract 4 on both sides. That tells us that a squared is equal to 7. Take a square root of both sides, and you'll get that a is equal to the square root of 7. I skipped a couple of steps showing them, but you should all know how to solve that Pythagorean equation by now, I hope. So that says the adjacent is square root of 7. There's actually 2 radicals in this right triangle. Nobody said they couldn't all be radicals. Nobody said they had to have a whole number anywhere. It's nice when they do, but they don't have to. So now we can finally find cosine of the angle. We can find the cosine because we know what quadrant we're in, so we know whether to attach a plus or a minus to this at the end of the day. And we also have the opposite, adjacent, and hypotenuse to find that correct ratio. So the cosine of theta should be equal to, and again, cosine is ca, C-A-H, adjacent over hypotenuse. The adjacent being the square root of 7. The hypotenuse being the square root of 11. And then I'm going to write a symbol here temporarily. It's a matter of which one do we choose? Do we choose the plus or do we choose the minus? This is not the plus or minus from the quadratic formula or the square root principle. I'm saying it's going to be an either or scenario. It's either plus or minus based on the quadrant. How do we know? We're in quadrant 4. Cosine is going to be, is it positive or negative in quadrant 4? A, smart, trig, class. C, cosine's positive in quadrant 4. If you don't believe me, cosine's positive. That's because we're going right. Cosine goes like the x value. So I'm actually going to leave this in here and say that it's quadrant 4, cosine is positive in quadrant 4. So this is going to end up being just square root of 7. Why did I leave that space there? Square root of 7 over square root of 11. And if you circle this, this is what's going to happen. It's wrong. Because there's a square root in the bottom, not allowed. But Mr. Beckner, you had it in your original problem, but that doesn't mean it was technically correct. Again, the sine, I really should have multiplied top and bottom by square root of 11 and gotten -2 square root of 11 over 11. But it would have made the Pythagorean calculation a little bit more of a pain. So again, this was in an incorrect form just to give us a little push. But our answer does need to be in the correct form, so we have to multiply top and bottom by square root of 11 to fix it. And we will get the square root of 77 in the top over the square root of 121 in the bottom, which is the square root of 77 over 11. If you skip the middle step and just say square root times square root is the whole number of 11, that's fine with me. But there's our answer. If for some reason our angle had been in quadrant 3, then this would have been a negative answer. That's the only difference there. So the first time we did the reference triangle first to find the missing side. Then we did the plus minus sign patterns. This time we did the plus minus sign patterns, and what I mean is SIGN patterns, then the reference triangle. Doesn't matter the order you do those two things. It matters that you do both of those. So here's what happens on a test. Nobody wants to do this plus or minus thing and figure out which it's supposed to be. So they just pretend everything's in quadrant 1 and they make all their answers positive and they get half of them wrong because of that. And that's a major problem. You have got to go through both of these ideas. This is the number one type of mistake students make on this first test, is they don't do this stuff right here, figuring out what quadrant you're supposed to be in, as well as picking an appropriate sign based on that quadrant, plus or minus sign, that is to say. Okay, so we keep talking about this reference angle and how we can use it to find trig functions. And we have basically been doing this right here without actually doing it. But how can we go from, say, an original angle of maybe 210 degrees to a reference angle of 30 degrees for that one in particular? How would we go from a reference angle of, say, 301 degrees, I'm sorry, I said reference there. How could we go from a regular angle of 301 degrees to a reference angle of 59 degrees? Or how could we go from an actual angle of 120 degrees to a reference angle of 60 degrees? That's what we want to focus on now. Converting to a reference angle. Not just drawing up the triangle and leaving it blank. If you know the original angle, we can now find the reference angle. There's 3 scenarios. You're either in quadrant 2, 3, or 4. Because quadrant 1, you don't need a reference angle. In quadrant 1, the reference angle is the angle. So when you're in quadrant 2, so here's your terminal side. Here's the point at the end of the terminal side, if you will. So going from here to here, swinging this way, that's our true theta. But this right here would be our theta prime. As a reminder, a reference angle must always swing from the x-axis. I'm going to scroll up to show that. A reference angle is the angle from the closest x-axis to the terminal side. You must always swing from the left-sided horizontal axis or the right-sided horizontal axis. You're never considering yourself swinging from a y-axis. You will never, ever, 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 ever see me put a reference angle here. If I put my reference angle here, read for wrong, because that's going between the y-axis and the terminal side. So that would be wrong. You have to swing from the x-axis. So when you're here, you're somewhere between 90 and 180 degrees for your actual angle. Going here, this might be 120 or 135 or 150 or 179. Your reference angle's got to be between 0 and 90. Well, the whole thing would make up 180 degrees. If you cut off the angle, that would give you the remaining bit, which is here. So your reference angle is equal to 180 degrees minus the original angle. Essentially what you're doing is you're taking 180, which is the whole half of a circle, and that sounded weird, whole half, and then you're, by subtracting off the angle, you're subtracting off this section, and it just leaves you with this wedge. That's the idea there, geometrically speaking. So when you're in quadrant 2, this is the, quote, formula, if you will, to find a reference angle. When you're in quadrant 3, so here's your terminal side. So your angle is swinging all the way across there. So something like 190 degrees or 250 degrees. It's between 180 and 270. So the reference angle, does it go here or here? Which one? We're supposed to swing from an x-axis. This would be swinging from a y-axis, so it's wrong. Your reference angle goes right here. There's your theta prime. So The idea before was we subtracted off the angle to leave us with the rest from those two things basically being supplementary angles. These two are not in that kind of position. The way you find theta prime this time is, this chunk is 180 degrees, so you're going to take the entire angle, you will take the entire angle here, and then you would subtract off the 180 degrees. So you take this bigger one and you subtract the smaller one, and that would leave you with this. So it's going to be the actual angle minus 180 degrees. And now you're probably annoyed because these two things are opposite of each other for when they're in quadrant 2 or 3. I'm going to give you an easy way to do this after we're done, per usual. All right, when you're in quadrant 4, now you're swinging almost all the way around. So that's our theta, the big go around, between 270 and 360 degrees specifically. So our reference angle is not here, it's not here, it's not there. That's swinging from the y-axis. It's here, swinging from the x-axis. That's our reference angle. It's like Pac-Man sideways, kind of. So how do we find that? Well, here's the idea. If we kept going all the way around, this would be 360 degrees. This is going to feel like the first one. Let's subtract off the original angle, and that would leave us with this chunk. So the reference angle this time, I'm going to put it above, because that's where the room is, would be 360 degrees minus the original angle. I have a typo somewhere. Sorry for this. Please, eyes on my mouse. This was a typo. Your reference angle was supposed to be the original angle minus 180, not the reference angle. That was a typo. I said it right, but I wrote it wrong. I think I said it right. I hope I said it right. So make sure you get this correction right here. When you're in quadrant 3, to find a reference angle, you take the original angle and subtract off 180 degrees. All right, so one of these versions you're doing 180 minus the angle, another one you're doing the angle minus 180, another one you're doing 360 minus the angle. You're never doing the angle minus 360. That would actually be to find coterminal angles, which you could call a coterminal angle or reference angle if it ends up in the appropriate size, but it doesn't always. So here is a cheat for this. Just take your angle and subtract 180 or 360 in an order that gives you a positive answer between 0 and 90 degrees. This will be the reference angle. How do you know whether to use 360 or 180? Whichever it's closer to. How do you know whether you should do 180 minus the angle or the angle minus 180? If you do it in one order and you get a negative, that means you did it the opposite way, just do it the other way. Or you can even just say, all right, well, if it's negative one way, it's positive the other, and just delete the negative. Reference angles should be positive. And again, this is how I do it. I look at the number, and in my head, I'll say, all right, I need to subtract 180 because it gives me an answer between 0 and 90. Or I'll say I need to do 180 minus the original angle because that gives me an answer between 0 and 90. Or I'll say I need to do 360 minus the answer because that gives me an answer between 0 and 90. If I've gone more than full circle, then I'd go the angle minus 360 because that would give me an answer between 0 and 90 if we were in quadrant 1 still. So I really do think what I typed out is extremely helpful because it's a trial and error process, and it's not like it's an extreme case of trial and error like factoring. It's just subtract a number in 180. If that gives you something between 0 and 90, you're good. If it's negative, delete the negative. If it gave you something too large, then switch your 180 to a 360. But some people like blatant memorization of formulas and ideas, so you have the method up there for them. So for example 3, let's find the reference angle. Referring angle, reference angle, third time's the charm, right? Reference angle, typing is hard. Remember, reference angles are going to be theta prime. You have got to get in good habits of labeling these appropriately. I know I'm a hypocrite since I accidentally put a dash there earlier and didn't mean to. But it is important to understand the distinction between an actual angle and a reference angle. All right. For A, we're going to start with 150 degrees. And these could be in radians as well. Spoilers for a later problem. So let's see, if I did this angle minus 180, I would get negative 30. So it's definitely not that. 150 is in quadrant 2, so it's definitely 180 minus the angle. And if you do 180 minus 150, you get 30 degrees. That's an answer that we expect. So that's the reference angle. You just got to get an answer between 0 and 90 by adding or subtracting 180 or 360. Generally not adding, but you could see some weird examples where it is. Let's do another. How about 300 degrees? So maybe you start out trying to do 180 minus this. It's going to be negative, definitely wrong. Swap it. Maybe you do 300 minus 180. So I'm going to write something that I'll erase in a second. 300 minus 180 would be 120. That's too big, man. Sorry, I was watching BoJack the other day. So if that's too big, that's not the way to do it. If it's too big, that means we probably need to switch it out to the 360. If you do 300 minus 360, it's negative, so it's definitely 360 minus 300. That'll give us our reference angle of 60 degrees. So an actual angle of 300 degrees, that was weird. An actual angle of 300 degrees is a reference angle of 60 degrees. C. Let's go with 225 degrees. And by the way, both of these 150 and 300 we'll see over and over and over and over and over. All right, 225. If I do 180 minus 225, negative, so that's not right. Swap the order. How about 225 minus 180? And if you tried 360, it would be too big. 225 minus 180 is 45. Bingo, that's in the window, so that's our reference angle. Oops. Finally, D, 7 pi over 3. Oh, radians, everybody's favorite. If you need to convert this to degrees, you would multiply by 180 degrees over pi. I'm not going to show you that. If you want to do it that way, that's your own prerogative. You do you. If you can get the answer right ultimately and get the reference angle, that's fine. But your reference angle is going to need to be in radians since it started in radians. Now 7 pi over 3, that's a pretty big number in terms of radians. In fact, I think this has gone more than full circle. So note that 2 pi over 3, I'm sorry, why did I do over 3? That 2 pi is the same thing as 6 pi over 3, just getting an LCD. 2 pi over 1 is 6 pi over 3, multiplying the top and bottom by 3, or saying 1 goes into 3, 3 times 2 is 6, however you do it. That 7's a little ugly. Let me just clean that up. 7, that is just bad. The pi is what's causing the problem. There we go, 7 pi over 3. 7's bigger than 6, which means this has gone more than full circle. So this problem is actually none of the written down cases, but I did verbalize it because we have gone 360 and then some more. We've actually gone another pi over 3, in fact, as we will see. So what we need to do is first find a coterminal angle, which means we need to subtract 360. So we got to take 7 pi over 3 and subtract 360 degrees, which is 2 pi radians. But we know that 2 pi over 1 is 6 pi over 3. 7 minus 6 is 1. So that's 1 pi over 3, writing it to be meticulous for the moment. Pi over 3 is between 0 and 90 degrees. If you don't trust that, multiply by 180 over pi and you will get 60 degrees. Something that I mentioned you should memorize, in my opinion. So pi over 3 is 60 degrees, so we're in the right window. That's our reference angle. So we actually subtracted 360 to get that because this was more of a coterminal situation than quadrant 1, 2, or I'm sorry, 2, 3, or 4 to find your reference angle. So your reference angle is just coterminal, and again, without the 1 written, pi over 3. Do it that way. Now, if you left this in radians, how do you know this is between 0 and 90? Well, 90 degrees is pi over 2. Pi over 3 is smaller than pi over 2. It's got a smaller denominator. All right, now we're ready for big boy problems, big girl problems. Example 4. Evaluate the trig functions. A, we're going to have the sine of 120 degrees. We did the sine of 30 and 45 and 60 last class in 5.2. Number 5.3, we're opening up to the full circle, all 360 degrees, all 2 pi radians, not just between 0 and 90, not stuck in a right triangle. But when we're using these bigger angles, we like to reference right triangles because things like 30, 60, 45 are all in here. So if we can take something like 120 degrees and turn it into 45 or 30 or 60 as a reference angle, then we can very easily do the opposites, hypotenuses, adjacents, and their ratios as appropriate. We just might need to throw in an extra minus sign somewhere depending on the quadrant we're in. That's what we're boiling this all down to. So this stuff right here, these 2 triangles as well as the smart trig class is going to be necessary for what we're about to do. First thing we got to do is find the reference angle first. Find the reference angle first. If you needed to draw this up, be my guest. That's what some people like to do. So we go 120 degrees would be in quadrant 2. So this right here is our, I'll label it in red just for emphasis, 120 degrees. That's our angle. So that was theta. Theta prime would be this segment right here. So this would be the reference angle because we're swinging to the terminal side from a positive x-axis. Again, if you swung this way, you're using the y-axis, and you don't ever use the y-axis to swing from for reference angles. So this looks like the 180 minus situation. If you try to do 120 minus 180, you'd get a negative answer. All right, so theta prime will be 180 degrees minus 120 degrees, which is 60 degrees. That's our reference angle. So what we can say is that the sine of 120 degrees should be exactly the same thing as the sine of 60 degrees, but plus or minus. Not both of them, it's one or the other. That's why I'm writing the or word to distinguish it from that quadratic formula idea. It's one of these 2 things based on the original quadrant. Since our original angle, that's original angle, not the reference angle, was in quadrant 2, and we're taking a sine, quadrant 2 we're going up, that's the y value, so the sine should be positive. So this is equal to, I'll write the plus for emphasis for now, positive sine of 60 degrees. And again, this is what other students want to do. They want to rush. They don't want to think about, oh, the quadrant makes it positive or negative. They'll just say sine of 120 is positive sine of 60. They just say that they're equal. But again, this aspect will make or break you over and over and over and over and over and over. You cannot forget that. How do we do the sine of 60 degrees? Well, we got to go back to our reference triangles. I'm not going to draw it up over and over and over. Here's the 30, 60, 90 triangle, which is the 1, 2, square root of 3 triangle. 1 is opposite the 30 degrees, square root of 3 is opposite the 60 degrees. I've already had a couple students emailing me about this, which one's supposed to be opposite, why am I getting these ratios backwards? We're not on the 30 degrees, we're here, we're 60 degrees, which for us right now makes the square root of 3 the opposite, that's opposite, let me spell it out, and the 2 is the hypotenuse either way. The 1 is the adjacent. We're doing a sine, so we need opposite over hypotenuse. So that would be the square root of 3 over the 2. You should probably draw these triangles over and over and over. Even though I'm not doing it inside of the problem, I've referenced it. Draw that up yourself. So this will be equal to, positive, I'm not going to write the plus sign anymore, the square root of 3 over 2. Again, where did the square root of 3 and the 2 come from? They came from the 30, 60, 90 triangle right here, where the square root of 3 was opposite the 60, the 2 is the hypotenuse. Square root's in the top, so that's perfectly fine. This is one of my favorite types of trig problems. I love these to death. You will see them in very numerous on the first test. You'll see it constantly throughout the semester. Trigonometry is all about balance. It's all about understanding that all of this stuff is related to each other. Quite honestly, trigonometry has like 6 types of problems to it, but we just do them in so many different ways and from so many different approaches. Hey, let's do it when we're in the first quadrant only. Now let's extend it to all the quadrants. Hey, let's do this idea, then let's extend that idea. So tangent of 135. So let's find the reference angle first. So let's draw up that stuff again. So 135, that's still going to put us in quadrant 2. You have got to know your quadrants based on degrees. So this is our theta, which is 135 degrees, which means our reference angle is going to be this small wedge again. There's our theta prime. So theta prime should be 180 degrees minus 120 degrees, which is going to be 45 degrees. Why did I write 20? 135. Where did the 20 come from? 135 degrees, and that's 45 degrees. I think I was looking right here when I said it. So our reference angle is 45 degrees. So the trig function at 135 degrees is the same as the trig function of 45 degrees, but plus or minus, maybe positive, maybe negative. We will have to establish that. So the tangent of 135 degrees is maybe positive, maybe negative. We'll establish that in a second. The tangent of 45 degrees. All their coordinates, their opposites, adjacents, hypotenuses, all the same. It's just based on the quadrant, maybe it's a negative answer instead ultimately. So since our original angle is in quadrant 2, that makes the tangent, is it positive or negative? We're in quadrant 2. Tangent is the ratio of y over x if you're thinking about it that way. Y is positive, x is negative, so that ratio would be negative. If you did a smart trig class, A is quadrant 1, S is quadrant 2, that says sine is the only positive thing in quadrant 2 out of sine, cosine, and tangent. Remember, the reciprocal functions share plus or minus aspects. So that also would tell us tangent's negative. So the tangent of 135 degrees is equal to the negative of the tangent of 45 degrees specifically. So we need the triangle that has 45 degrees in it. So we load it up, we redraw it. If we feel the need, you probably should feel the need to redraw that 45, 45, 90 triangle, which is right here. Draw these things until you have them memorized. Draw these things until you're absolutely getting the 30 and 60 and 90 and 1, 2, square root of 3 all in the correct positions. Because if you make this page when you start your test, as soon as you start your test and you swap the 30 and 60, you're going to get a ton of answers wrong if you do everything else appropriate to it. All right, so tangent of 45, TOA, opposite over adjacent. Opposite's 1, adjacent's 1, so the tangent's 1 over 1, which is 1. I'll be specific for now. Opposite was 1, adjacent was 1, but we have the negative because of being in a different quadrant, which makes this whole thing equal to negative 1. We might actually not finish this section today. Wow.
We are definitely not finishing this section today, obviously. And obviously also ignore that due date you see creeping in the corner. I think I mentioned earlier, sometimes I just leave those in my documents without thinking about it. Your due dates are here. So when we come back next time, we'll have a C from that section. We'll also have a D, might even have an E. I'm trying to remember off the top of my head, and my notes are, my dog is laying on my folder of my notes right now, unfortunately. So I can't see, but that is it for the day. So again, we have not finished 5.3, although I do advise you to go ahead and start that homework. And if you're not even going to start the homework, start writing things over and over if you're a person that learns that way. Like I said, draw that 1, 1 square root of 2 triangle many times. Draw the 1, 2 square root of 3 triangle many times. Do the smart trig class or drawing out the quadrants with the signs of your X's and Y's and the ratios and all that stuff, because however you're going to get the job done, that's fine as long as you have a way to get the job done. But besides that, have a good day. We will see you on Thursday. Make sure you've got 5.1 and 5.2 done by before midnight of Thursday. And if you have any questions, per usual, please email me. I hope this was a good learning experience, and we will see you Thursday. Take care.